Welcome, and thank you for joining this IRISS webinar supported by Data Centres Ireland, Data Centre Reliability and Safety by Design. As this webinar is pre-recorded, we will not be able to answer your questions live. However, if you do have any questions, please put these in the chat box and Mark from IRISS will contact you directly with the answers after the webinar. This webinar is being recorded and will be uploaded to the Data Centres Ireland website, where you can also view other on-demand content. If you would be interested in hosting your own webinar using our platform, please contact myself on kirstenhill@stepex.com. Once again, thank you for joining, and now over to Mark.
Thanks, Kirsten. Hello, everybody. Thank you for taking time out of your busy schedules today. It's really appreciated. But for the next 30 minutes, you'll learn how our regime of inspection has been simplified through innovation. Time and money has been drastically reduced with today's technologies and what's available. Safety and resources have taken the other direction, so they've drastically increased in how people can actually inspect their assets. What took an hour, day, or a week now can really take minutes, a day, sorry, even an hour or even a day on that. So that just gives you an idea of how quickly you can inspect and how often you can do it. Before I hand over to Martin, though, what I'd like you to think about is your current regimes. Okay, what are your challenges? Can you think of a better way of monitoring the condition of your assets? Is there a time to do this more frequently? Okay, do you perform them in-house or outsourcing? What is your expenditure on that? Is it you don't do them because there is no time, or you have to organize it and it takes a lot of energy to and man hours to actually inspect and organize that shutdown? What information do you get from your current regime? Is it useful to determine the condition of the asset? That if you can think about those whilst you look at it, look at this webinar, understand the webinar, and then if you have any questions, objections even, or suggestions, we welcome any discussion on this. So if you could just write anything you can in the box below, we will answer them as quickly as possible after the webinar, either today or certainly over the next couple of days. We can get round to you on that. But then also, if you want to follow that up, we can have discussions online. We can even arrange visits later on in the year when things have calmed down with the pandemic. But again, I thank you for your time. I'd like to hand over now to Martin. Martin, over to you.
Good morning, and thank you for joining us on today's webinar. My name is Martin Robinson. I'm the CEO of IRISS, where we specialise in designing safe and reliable electrical systems for condition monitoring. So this presentation that we're going to go for, this webinar, we're going to sort of go over some of the high points around designing safer and more reliable electrical systems. So before we start, we need to consider a few things. What strategy was used to formulate your current maintenance program? Was it based on an OEM's recommendations? Is it based on time-based, calendar-based schedules? Or is it based on a reliability assessment of the equipment? So how was that, your program, formulated? Is your current operational redundancy then based on, obviously, your maintenance strategy? Do you think that more reliable assets will impact redundancy requirements? And therefore, if you could reduce your redundancy levels, how much would that be worth to your organisation? And when was the last time you reviewed your current planned maintenance program? And have you ever completed a planned maintenance optimization study? So just keep those in mind as we go through the presentation. So I'm going to go over some interesting statistics and the latest the data center study from the Uptime Institute. Now, we all know that more and more data centers are being built every year, but the thing that really is concerning is that the respondents to the report basically stated that last year was 25% of them had seen some type of downtime incident. Well, that's actually increased to 31%. So not only is the amount of data centers we're building increasing, but so is the amount of downtime incidents we're seeing. So We need to be doing something about this. On-premise power failures are the most common. 80% indicated that their most recent outage could have been avoided. The time to full recovery for most outages was between 1 to 4 hours, with over 1/3 reporting that their recovery time was over 5 hours. And IT equipment failures are not the main culprit. They only account for about 4% of outages. So the cost of failure really is massive. So a report by Gartner said the average IT downtime is about $5,600 a minute. Now, obviously there are a myriad of organisations with different operating costs. So these costs can be huge. So, we're saying that, an average downtime at the low end could be as much as 140 grand, up to at the high end $540,000 per hour. I mean, these are crazy figures, but those of you in different industries would actually recognise these as being your norm. 98% of organisations saying a single hour of downtime could cost them in excess of $100,000. Over 81% of respondents indicated that 60 minutes of downtime would cost their business over $300,000, and over 33% of those enterprises reported that 1 hour of downtime could cost their firms as much as $1 to $5 million. So we'll see failure must be avoided at all costs. So there are several high-profile incidences of failure, but the big ones for me were Delta Airlines. Their loss was estimated at being over $150 million. But the big thing is, it's not always about money in some respects. I mean, it's about goodwill, your customers' confidence in your ability, etc. But Wells Fargo, that was the big one. The multi-day outage that Wells Fargo has seen actually cost their stock dropped by nearly 1%. Well, that's massive. Massive. So again, it just indicates what we're trying to do with getting rid of failure. So the top 5 challenges faced by data center managers: you need to maintain availability and uptime, we know. You need to improve utilization of capacity for power, cooling and space. Obviously, you're always trying to reduce operating expenses, you're always trying to manage the energy usage and costs, and you're always trying to improve your staff productivity. So I think by the time we get through this presentation, you're going to realise that if you adopt a robust reliability program, it's going to impact all of the above and more. So reliability, what is reliability? Well, reliability is a number of things that you have to be looking at. So we're looking at design, purchase, storage, installation, startup, operation, and maintenance. Now, all of these areas, all of these business silos will inject defects into the system. So what we're trying to do in reliability, if you like, is defect elimination. If we can impact the defect elimination, then rates and losses and downtime, unneeded work and injuries are all reduced. And that means if we reduce those, we actually increase our asset utilization and necessary work. So then we're going to get minimum cost for maximum product. But you can see that maintenance is a very small part of this. You can't maintain your way to reliability. So you need to start thinking about reliability as a complete mindset change. And those of you who've been around ISO 55000, the asset management platform, you can see it's all about defect elimination in every area. So if we design put right, we purchase right, we store right, we install and start up right, and we operate with care, and we maintain with precision, we're going to impact those defects, and that's going to give me better asset utilization. So planned maintenance optimization program. This is where I always like to start. I just, you can't fix something if you don't know it's broken. So the first thing you need to do is look at your planned maintenance and what we call a PMO program. So don't assume your PMs are correct. They could be wrong. Now, this is an analysis of 20,000 PM tasks that was conducted. And basically, we've seen that 11% of those PM tasks could be used as is. 8% could be deleted altogether. That's 1,600 tasks. Get rid of them. Yeah. 33% could be replaced with some sort of condition monitoring. Okay, so that's 6,600 tasks. We could re-engineer 26% of them. 7% can be transferred to operations, and 15% can be transferred to lubrication. So these are massive, massive numbers. So again, please don't assume that because you're doing a PM, it's the correct PM. It probably isn't if you haven't actually looked at this. A lot of legacy tasks do get carried over. And also, don't assume your vendor PMs are correct. This was a review of the vendor PM's recommendations of 964 tasks which were analysed. Now, basically, what we're seeing there, 38% were perfectly adequate, could use as is. 21% could be deleted altogether. 23% could have an extended interval. 12% actually needed new tasks, okay? And 6% could be a reduced interval. So again, massive implications on the amount of work you're doing, especially with a shrinking workforce available to you as shrinking resources. But this was a good thing. Out of this study, we actually found 96 new failure modes that weren't even being addressed altogether. So the risk of those, so just look at 10%. Okay, a 10% increase in tasks that were never being done, that meant that your risk of failure was increased exponentially. So random failures, things fail randomly, nothing fails as is. So this was a study done by Winston Leday where we ran 30 components in identical circumstances and they all failed in different ways. Now, if I take redraw that histogram, we can look at the slopes, and the slope is what we've got mean time between failure, those of you who've done it. But we're looking at the average slope of failure. You've got a 5-day failure, 10-day failure, and then you have the anomaly, which you're always going to have in any data set. But if I'm maintaining to a 5-day failure slope, then I'm over-maintaining most of my assets. Yeah, if I'm maintaining to a 10-day failure slope, then I'm under-maintaining some of my assets. So it's a very, very important point to make, that things fail randomly. So that's why time-based maintenance just doesn't work. Yeah, there were 4 major studies completed on reliability center maintenance. The first one was United Airlines, the Nolan Heap study. Then with the Bromberg study in '73, and then the US Navy did 2 studies in the 80s and 90s on surface and subsurface ships. Now, all of the results from those were surprising. The results from the studies were surprising. I mean, I'm a mechanical guy by background, and I was always taught the bathtub curve was how things failed, but the time-based failure curve. So, but if you look at these time-based failure curves, you can see that the level of or the amount of failures that are time-based are very low in comparison to those of random failure curves. I mean, the biggest one of which is infant mortality. Now, the US Navy, from their studies, I mean, now, that you can see that they've got a significant reduction in the infant mortality and an increase in the random failures, but a significant reduction in infant mortality. And that's primarily because they use a lot of condition-based and they use precision maintenance techniques. So they fix it right the first time and limit the amount of failures seen in the field. So again, random failure curves is where most things break, and infant mortality is the big one. Now, there's ways that we can fix that. So traditional electrical maintenance practices, we utilise intrusive work practices, so tightness testing, mega stress testing, circuit testing, load banks, etc., etc. These are all sort of done, but to basically, I mean, why do we do the maintenance? We want to confirm that the circuits and connections are safe, and we want to confirm that it's meeting its operational requirements. So primarily we do that maintenance and testing to prove that to ourselves, okay, and to show legislative bodies that we're actually taking care of it from a safety standpoint. But there is a better way. If I can prove to you that all of the connections and circuits are safe and it's meeting its operational requirements and never shut down, then that's a significant step forward. So different types of maintenance strategy. Obviously, there's reactive, which is run to fail, which is perfectly adequate for non-critical assets. We have preventative or time-based, predictive, which is a terrible term, which is for condition-based. Now, I don't like the term predict. I can't predict anything. Yeah, I can trend failures, I can trend performance, but that should really be known as condition-based maintenance, and then proactive maintenance, or root cause-based. So if I see a bunch of failures, I'm going to go back, try and find out why they're failing, and then bring in some sort of preventative action to make sure that doesn't, or an inspection technique or whatever, to make sure I'm going to find that before it fails again. But again, remember, maintenance is a reliability function, not a repair function. Yeah, reliability is not just about maintenance, which we went through earlier. It's, reliability is about defect elimination. So if you look at the effects of time-based maintenance, so like here's a typical bathtub curve, and these are my time-based maintenance schedules. So you can see I'm doing a whole bunch of maintenance when it's not needed. Okay, it's just a waste of time, money, and effort. The asset is running as required, delivering its output. It shouldn't really be touched. When I should be doing maintenance is here, yeah, at that point of potential failure, where there's a change in performance. If I conduct the repairs, yeah, the remediation at this point, then I've saved a whole bunch of shutdowns for unnecessary maintenance. Okay. So if you think about planned time-directed maintenance, basically what I'm saying is it's not broke, but we're going to fix it anyway, which is ludicrous. Okay, ludicrous. And then we need to sort of think about, again, mindsets, etc. But, you know, if it wasn't broke, but it fixed it anyway, it just doesn't make sense to anybody. So if you look at the effects of time-based maintenance on infant mortality, every time I do maintenance, I reset the infant mortality clock. That's why those things are so high, those infant mortality failures. So why am I doing unnecessary maintenance when I can inject defects through human error and see failures thereafter? So again, I don't want to be touching it. So if your installation startup, if you think about what we see, the greatest risk of failure, defects and failures, is at startup. So how can we minimize that risk? Do less shutdowns. So installation startup, Roman Hesse, you're 7 to 17 times more likely to introduce defects during startup. Yeah, BP incidents are 10 times more likely during startup. And chemical industry reports safety incidences are 5 times more likely during startup. New equipment can have twice the number of infant mortality defects as existing equipment, and 92% of rotating machinery is reported to have defects at startup that result in premature failure. So if you look at maintenance strategies, as much as 68% of failures are due to infant mortality. Therefore, we've got to improve how we design, buy, store, install, start up and shut down our equipment. We must avoid unneeded maintenance, which can restart the infant mortality failures. As much as 80 to 90% of failures occur in a constant yet random mode. Therefore, we must monitor the condition of processes and equipment to determine what's going on and when they're going to fail. Yeah? Note that 77 to 91% of equipment has no end of life. Most of the equipment that you change or replace is an upgrade. Yeah? Very, very few things are changed because they're broken. Okay, so remember that. So if you look at a condition-directed repair reliability program, which I know is a mouthful, if it ain't broke, don't fix it. What is broken is the way we manage our assets. Okay, unnecessary maintenance. Yeah, maintenance-induced failure. These are things you're going to hear time and time again. So fun fact, yeah, the Mars lunar rover was designed by NASA to last 90 days. So how long did it last? 14 years. Why? Because we have no mechanics on Mars. There's no one there touching it, okay? It was designed to task. It was designed for reliability. It was designed to do its job. It did its job and some. And the only reason it did fail is because the batteries couldn't recharge anymore. So where to start? Change the way you think, please. You can't fix a problem with the same mindset that causes it. So you really I really want you to sort of give yourself a clean whiteboard and just change the way you think about things. Question everything. So designing for safety and reliability. Yeah, I say I'm ex-military, and we were taught the KISS principle. Yeah, KISS, keep it simple, stupid. Now I'm not saying that everyone's stupid. What we're saying is the KISS principle is about taking very, very complex scenarios and simplifying them. Okay. So basically, as Einstein said, it means that you should simplify the design of a product, and success is achieved when a design is at its maximum simplicity. The process could be super complex, but the design needs to be at maximum simplicity. So when we look at mistake proofing, Japanese have a great term called poker yoga, mistake proofing. So I want to try and get you to start thinking about the tasks that need to be done and how can we design them that they're done more effectively and safely. So design for safety and reliability, or DFSR, prevents defects in our everyday condition-based maintenance activities and processes. Yeah, errors should be considered inevitable. Any type of error can be reduced considerably, if not eliminated altogether, utilising DFSR strategies. DFSR creates safer work environments. It assures consistency and quality of results, makes problems more visible, and lowers the cost of design and manufacture. Different types of DFSR, lockout tagout. Lockout tagout is a DFSR protocol, it's a process. DFSR is not always about an assembly, it's about a management process, it's about a protocol. So lockout tagout is a DFSR solution. 3-pin plugs, you should only be able to put a plug in one way. I know we've all had people try and do it differently, but the plugs are designed to go in one way and they're safe. Okay, if you look at infrared inspection windows, ultrasound sensors, all sorts of things. These are inspection points where you can get into the assets safely and effectively without putting yourself in harm's way. And even McDonald's has a bun height gauge, so they're basically ensuring quality, in everything. People that eat Big Macs routinely, if it feels too thin, you feel like you're being cheated. It never looks the same as the pictures, but as long as it feels the same, you're happy that you're getting the right amount of meat, etc. in your burger. So again, it's quality. So safety, quality, manufacturing processes. Designing for safety and reliability. Now, reducing maintenance-induced and safety failures. Now, in America, we've got the NFPA 70E, and there's a whole section on maintenance-induced failures. But how can we reduce those? So if you look at electrical safety, it's super, super dangerous. Now, this is an overall safety curve. It's from Heinschel in the 1930s, but the ratios are still the same today, where you're looking at 300,000 at-risk behaviours, can lead to 300 recordable injuries, can lead to 1 fatality. And that's in your overall workplace health and safety. Now compare that to the electrical safety, in the electrical injury, where we're saying for every 10 recordable injuries, you can have 1 fatality, which that means that so it only takes 10,000 electrical at-risk behaviours to kill an electrician on these ratios, which is unacceptable. Absolutely unacceptable. So we have to reduce the amount of at-risk behaviours, okay, by designing our systems to maximum simplicity. So hierarchy of controls, those of you that are in health and safety, etc., or risk management, basically the holy grail is elimination. We want to try and eliminate the hazard. If we can't eliminate, we can substitution, engineering controls, administrative controls, or PPE. But notice PPEs are the least effective, and use the most. Now, please, I am not a PPE basher. We need PPE, I know we do. But if we can eliminate what would the issues, if we can eliminate the risk as best we can through DFSR strategies and condition-based maintenance, this is where we're working. We're working in the elimination and substitution space. This is the most effective area to be with. Some data here. Again, I've got a lot of data from the Ron Moore. Wrote some great books on this subject. But you can see this is a correlation of corrective and reactive work orders with injury rate. And notice the more corrective and reactive work we do, the higher the injury rate. Why? Because everybody's running around like a headless chicken and there's no planning involved. This is totally reactive. If you look at the total recordable injury rate versus reactive maintenance, again, the less reactive maintenance, the lower the injury rate. Go figure. Correlation of condition-based maintenance work orders with injury rate. The more condition-based we do, the less injuries we do, because we're looking at planning. We're looking at basically taking data, and on the basis of that data, we're doing shutdown, repair, mediation work. So again, less injuries, higher productivity. So how do we manage the risk? Like recalculating what we call a risk priority number. So calculating risk, so there's so many different ways of doing it. Every organisation will have its own way of doing it. This is one that I use. It's no better or no worse than probably the one you use. But we look at 3 areas. Severity, from 1 to 10. The probability of occurrence, from 1 to 10. And how easy is it to detect, from 1 to 10. So from severity times occurrence times detection, we come up with a risk priority number of anywhere between 1 and 1,000. So once we've calculated the risk, we then put them on, this is a heat map. Again, I like working on heat maps. Some people like working on matrices, you know. So I'm just talking about the processes here, okay? The way you do it is up to you. But once we've laid out our risk matrix, if you like, or heat map, then we want to ask ourselves this question: what is our risk appetite? How much risk am I prepared to take? Now, one of my biggest bugbears in the data center world is about criticality, you know. So your risk is always based on criticality, but there's an old saying: if everything's important, nothing's important. Everything can't be a 10. You have to really understand your criticality, and then you can ask yourself this question: what's my risk appetite? Now, once I know my risk appetite, I can outline some maybe inspection and repair time-based timeline inspection. How often am I going to inspect it? What am I going to do, etc.? Am I going to go to full IoT-based solution? Am I going to do an annual inspection? I might even decide to run to failure. Yeah, this is when I need to understand my criticality, etc. But risk appetite is important because remember this: the higher your risk appetite, the lower the cost of reliability. The lower your risk appetite, the higher cost of maintaining that reliability. So really understand it because it has significant implications on the financial requirements. Now, severity I can't really do anything about. Severity is operation, it's criticality, so that's going to be driven by operations. But I can do something about occurrence because I can look at I can inspect the systems more routinely, and I can do something about detection because I can design for safety and reliability, like an inspection window, a sensor, a technology, a management technique, or etc. I can do something here. So therefore, if I can do these two, it doesn't really matter about the operation severity because I can engineer the risk. So that means that I can basically bring them all down into what we would class as acceptable risk level. And still do a lot less maintenance. Another problem you're going to have, and everybody's having, is bridging the skills gap. We cannot find the skilled engineers that we currently need. It's getting harder and harder. Yeah, this is the results of a study from Forbes. But basically, I mean, just looking at the electricians on the bottom here, we have 27% over the age of 55 and 57% over the age of 45. Now, a lot of these guys are coming up to retirement, early retirement, although we're trying to keep them as long as we can. And we haven't really backfilled the skill sets to fill in behind these guys. We're doing something about it now, but there's going to be this concertina effect. So that's why technology is becoming more and more and more important, because we need that to infill the skill shortages that we're currently seeing ourselves in. Another thing you've got to remember is total cost of ownership. Again, you know, when I got into asset management, I really started to understand TCO. But, you know, if you look at the acquisition, research, design, production, test, and construction, that's really the tip of the iceberg, literally. You know, the indirect costs, the operations, maintenance, testing, support, spares, etc. That's where the money is. So, you know, you can see in some industries, it's probably 15 to 25 is an average on the direct costs, but up to 85% is indirect. That's the running of the plant or the data center or whatever you're working on for the 15 or 20 years or 50 years, however you're going to run it. That's where we spend all of our money, on the indirect costs. Now, if I can impact operations, maintenance, testing, support, spares, etc., by designing for safety and reliability, doing a lot less maintenance, using a lot of things, then that's a big number. And that part of it can be responsible for up to 75% of invisible costs or indirect costs. How much can I impact that to? It can be a big number. This is something that was shared with me from Ramesh Guliati, Jacobs Engineering. But what they showed, I mean, obviously, if you come from design, you get your maximum return on total cost of ownership. Yeah, but they've shown a significant, up to a 40% reduction in TCO if you take this from design. Now, obviously, your ability to impact TCO diminish as you move through the life cycle, but there's always going to be opportunities to make significant savings. But total cost of ownership, yeah, the impact on total cost of ownership by getting into a DFSR solution in the design and planning phase is massive. A man-hour analysis. This was a data center, 250 critical assets, inspected, fully energized annually because of obviously it was because of the implications of what was done. 2 site electricians and 1 contract CBM engineer. Took about 200. It was about 250 hours to complete. PPE suit up times for the engineers and the electricians for panel removal was 126 hours. The man hours for the inspection, so you had sort of 250 panels to be opened, etc. Half an hour per panel. The CBM inspection was 25 hours. It was 6 to 10 minutes a panel. Cover replacement, another 250 hours. The CBM engineer waiting time, so the thermographer and ultrasound guy was sitting there for 250 hours watching the guys removing panels and replacing panels. So and then you paid the electricians 50 hours just to watch the guy do the inspection. But the total inspection was 825 hours plus the PPE, 951 hours. These are massive, massive numbers. Now, this is the important one. That's what we're trying to do here. Just the inspection, which was 2.6% of the total labour, okay, that was done for this inspection. The remaining 926 hours was dangerous, high risk, unproductive labour. Doesn't make sense in any way. So this is where these programs start to pay for themselves, because we can get rid of that chunk of unnecessary labour. And imagine, and then we do a lot less of it. So once the DFSRs was in, because there's no need to shut down, there's no need to pit for the PPE. There's no cover removal replacement. The CBM inspection was actually increased to 30 hours, but that included writing the report. In fact, in this area, we did the whole inspection in 7 hours, but we added the additional hours for report generation, etc. Upload to the CMMS, work orders, that type of thing. So again, 30 hours, but 100% safe, productive labour. Okay, 97% real world savings, massive, massive numbers. Cost of, this is some more data where we look at the maintenance cost versus reactive maintenance. Okay, the more reactive maintenance, the higher the cost. Okay, guess it's no surprise, no surprise. Here we show maintenance cost versus condition-based maintenance. Again, the higher the level of condition-based maintenance, the much lower the cost of maintenance as a percentage of asset replacement value. Okay, so again, it just the numbers are there and they totally make sense. Another area now we're considering, how do we reducing our carbon footprint? Obviously, increased equipment reliability through reduced time-based maintenance has significant impacts on your carbon footprint. Okay, so again, these are the sort of things that are absolutely driving how we, the efficiency and reliability of our equipment, because of the impacts on our carbon footprint is massive. Plus our extended carbon footprint. If we're doing less maintenance, we've got less support, we've got less parts, we've got less spares, we've got less people getting involved in doing that. Okay, we're just really, really driving the system. So if you look at the effects on these programs, we have increased safety through hazard removal, increased ability to anticipate and plan for repair and intervention tasks. You can have increased time in service, decreased need for intrusive maintenance tasks, inspections, replacements, etc. Reduced cost of maintenance in terms of manpower and expenditures for replacement parts, reduced collateral damage potential for degradation remediation, and they reduce total cost of ownership. So it's a win-win-win all down the line. Love this saying by Deming, but it stands true today. Without data, you're just a person with an opinion. It's the data that should drive our decisions. It's the data that should drive the way we manage our assets. So thank you very much for taking the time, for listening to my webinar, and now we'll take questions. Thank you.
Well, thank you all for coming. If there are any questions, please feel free to either post them on the wall here, or we will send out a recording of this presentation to you all, and then please get in touch direct with us. Okay, thank you very much, and have a great day. Bye for now.